All right, this is assignment 7. This is dealing with a particular equation that helps define exponential growth and exponential decay. So let's go ahead and talk about that just a little bit. So what I'm going to do is I'm going to kind of explain what exponential growth and decay is at first. All right, so what exponential growth looks like is kind of like a skateboard ramp. All right, it's kind of like the skateboard ramp. And so we start off technically when x is equal to 0, and this is in essence an initial amount. And you'll notice that what is happening in exponential growth is early on, you're not growing a whole lot. All right, you're not growing a whole lot from one point to the next. All right, you may, grow a little bit, but as this time continues, the amount of growth greatly increases from one step to another. So here, from like 0 to 1, you may have grown like 2 or something like that. Think of it like a bank account. Your bank account may have grown $2. Okay, big deal. However, from 1 to 2, though, oh man, that's a much bigger growth. Like I think that you may have grown $10 in that situation. Oh wow, that's great. And then 2 to 3, wow, I really took off here, and I grew 25 or something like that. And so this growth greatly increases, greatly increases. Okay, and so this is an idea of an exponential growth. Okay. Now decay is similar to this. Decay is similar to this. Right? Decay looks something like this. Okay? Where at first, the amount that you're going down is drastic, but then it gets smaller and smaller and smaller and smaller and smaller. All right, so it goes down. You start to go down like crazy fast, but then the amount that it goes down decreases, and that's called exponential decay. And oftentimes, things that are described by exponential growth and decay are like populations of things. Okay, like populations of things. Like the idea is, okay, you start off with 2 bunnies. Okay, you start off with 2 bunnies, 2 rabbits. Okay, there's 2 rabbits. Okay, and then those 2 rabbits are going to multiply. Let's say that they have each 2 rabbits. Okay. All right, and so now we have a grand total of 6 rabbits. But then these rabbits are going to multiply. And now we have a grand total of 6 plus 8 is 14 rabbits. Okay, now we have 14 rabbits. And then these rabbits are going to multiply. And you can see that the amount of rabbits are going to crazy explode. Where at first, it's a manageable number of rabbits, but think about it when it gets like way down here in time, and the population of rabbits are just exploding every single year. Like, well, we got 5 billion more rabbits today. So that growth is crazy large. That growth is crazy large. Okay, and another is explaining like population. Think of like bacteria. Think of bacteria on your hands. All right. So let's just say we got done, making a meal, and we have bacteria on our hands. It's a goofy looking hand, whatever. And so the thing is just teeming with bacteria. All right, you have a bunch of junk on your hands. Okay, Well, you wash your hands. Okay? And so a population of bacteria, let's say 1,000 or something like that, will be greatly, greatly decreased. Okay, so let's say it gets cut down to 500. All right, and that death continues on, so half, and then that would be 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 half. The idea. All right, so at first, the number of bacteria are going down a large amount. Okay, you're killing bacteria like it's a job, but eventually, is all of the bacteria going to actually be gone from your hand? No, all the bacteria is not going to be gone from your hand. There's still going to be some there. Okay? There's still going to be some bacteria on your hand, but so you'll be able to kill a bunch of bacteria, but that number of bacteria, that descent will slow down. And so that's exponential decrease, where at first it's really fast, but then it slows down. All right. Now, an equation that really helps kind of describe this is problem number 1. Okay. And here we have a of t. Okay, think of that's not a times t. This is like a single variable, right? So the amount, in essence, is a 1 plus r to the t. Okay, so a lot of these things are self-explanatory, what these variables mean and things like that. Like rate. Rate is the letter R in this situation. R is the rate. Now note that R is going to be a decimal. R is going to be a decimal. So that means if something says, oh, there's a 5% growth rate, that is the same thing as thinking of R as being 0.05. Okay, so think of it as being a decimal. R is 0.05. The initial amount is the letter A. So whatever you started with. There were 1,000 bacteria on your hand. You initially invested $2 into the bank. Things like that. There was initially 2 rabbits. All right. The number of time periods. All right. And that is the letter T. The number of time periods. And now that could be a bunch of different time periods, but that is one time period. Like, so if you're talking about years, that would be 1 year. If you're talking about days, it would be 1 day. And last but not least is the amount after the time that you spent. The amount after that time is the A of t. Okay, so comparing this number 2 to this original equation. Okay, this equation says f of x, which is, okay, so that's our A of t, 3, okay, 1.04, okay, that's a little odd, to the x. All right, not a big deal. All right. The first question is this exponential growth or decay? And so where that is found and how you determine that is this inside number right here. Okay, if this is growth, okay, that means this number is going to be greater than 1. If it's decay, that means it is going to be less than 1. So here I see, oh, this is bigger than 1. So this is going to be exponential growth. Okay, now what is that rate? Well, how much bigger than the number 1 is that number? Well, I see that's 0.04. 0.04, it's bigger than 1 by 0.04. So that implies that that is 4%. No decimals to numbers, there are decimals to percents, percents to decimals, et cetera, et cetera. And then what was the initial amount? That's that outside number, and this was 3. So we started with 3, and we have a growth of 4%. All right, same type of questions. Is this growth or decay? Again, this is growth, because that inside number is bigger than 1. Okay, how much bigger than 1 is it? Well, it's 0.77 bigger than 1, so that means the rate is 77%. What was the initial amount? That's the outside number. That was 22. So I started off with 22 somethings, and I have a 77% growth. Okay, number 4. Is this growth or decay? Again, this is growth. Okay, again, that inside number. If it's bigger than number 1, okay, it's bigger than 1, that means growth. If it's smaller than 1, that means decay. Okay, this is growing, this is growth. Okay, what is the rate of growth or decay? How much bigger than the number 1 is that? Well, it's 1 bigger than 1, or AKA 1.00. So that means that is 100%. That's 100% growth. What was the initial amount? That's the outside number, and 0.25 was the initial amount. All right, is this growth or decay? This is decay. Again, look at that number. That number is smaller than 1. Okay, how much smaller than 1 is it? Let's just do a basic subtraction. 1 minus 0.92. That is 0.08 smaller than 1. That is 0.08 smaller than 1. So what is that? That is an 8% decay. That is an 8% decay. What was the initial amount? It's that outside number, 11. So that one was smaller than 1, meaning it's a decay. How much smaller than 1 was it? It is 0.08 smaller than 1, which is the same thing as saying 8%. Okay, here we go. AT is equal to A, 1 plus R to the T. You invested $500. That's a start amount. So I started with $500 in a savings account at the end of 6th grade. The account pays 4%. So the rate is 4%. 4% growth. Okay. Using this, write the function. So the amount that is in your bank account is the initial amount, 1 plus R. So that would be 1.04 to the T. How much money will there be in your account at your high school graduation? So let's just do the simple math. So at the end of 6th grade, you made this investment. All right, so at the end of 6th grade, okay, so at the end of 7th, at the end of 8th, at the end of 9th, at the end of 10th, at the 11th, at the end of 12th. This is when you withdraw money. So here's where we started. So that was 1, 2, 3, 4, 5, 6. Okay, so that means that T is 6. Okay, so how much money is in your account? So what is the amount of money in my account after 6 years? And there would be $632.66. Not too bad. $132 growth. It's pretty good. Imagine what would be in your account if you let it stay there longer. Okay, so the population of lizards decrease at a rate of 2%. So the rate is kind of like negative 0.02. So they decrease at 2% per year. You counted 75 lizards in your habitat. All right, so the initial amount was 75. Okay, is this exponential growth or decay? Obviously decay. What is the rate of decay? 2%, okay, which is 0.02, smaller. What was the initial amount? 75. What is the function? So start with the initial amount, and this is decay, so this would be 2% down from 1 to the t. How many years will it take for the population to drop below 50? Okay, drop below 50. I'm going to use my calculator on this one. Okay, so let's graph this guy. So right now we have 75, 0.98 to the t. I'm going to call it the letter x. Okay, and then what I'm also going to graph is I'm going to graph the number 50. Maybe not. I don't know why, but I had to say y is equal to 50 or something like that for that thing to graph. Okay, so here's our lizard population. It starts off at 75, and so that's right there, okay, 75. And then we truck on along, and we have lizards, et cetera, et cetera. Oh, okay, sorry. So we have these lizards, and then they will run into each other at 20.07. Okay, so all I did is I graphed a population of 50. And I graphed the right-hand side, I graphed the left-hand side, and it runs into each other when t is equal to 20.05. So that's where we go from over 50 to under 50. And so when will this occur? This is close enough to 20 years. All right, Kikui is offering a sale on its laptop computers with 20% discount off its original price. There's an 8% sales tax added to the discounted price to get the final price to the computer. If X is the original price, Y is the final price. What right there, the equation to determine the final price of the okay. Here we go. So think about how much you pay when you get these discounts or these benefits and things like that. Think about what percentage you pay. So, for instance, if I have this sticker price, okay, but I get 20% off of that. Okay, I get 20% off of that. Okay. Don't think about the amount that you don't pay. Think about the amount that you do pay. So if I get 20% off, that means I have to still pay 80% of that. I still have to pay 80% of that original price. If I have 20% off, that means I have to pay 80%. Okay, so let's start there. How do you take a percentage of a number? You multiply. So if I know that of this original retail sticker price, okay, I have to pay 80%. That means I pay 0.80. So far, this is the price of my computer. Okay, I guess that should be Y. Y is the final price. Okay, so I get 20% off. So that means I pay 80%. So if that original price was 100, or excuse me, like say $500, I am now paying $400 because I got 20% off. Okay, but now, okay, we finalize our sales price, and the sales price is, again, let's say that $400. Let's say we know what that is. Now we have to pay taxes on this, and there's an 8% sales tax. So that means whatever 8% of this 400 is, okay, whatever 8% is, we have to pay an additional 8%. So of 400, what percentage do you pay? So of 400, if I have to pay an additional 8%, that means I have to pay 100% of that $400 and an additional 8%. That means I pay 108% of whatever that sale price is. I pay 108% of whatever that sales price is. So what we have right here is the price with our discount. So we need to pay 108% of that. This will be the final price of our computer. So if the sticker price was, let's say $600, we're buying a $600 computer. We get the 20% discount, but then we have to pay tax on it. And so the final sticker price of this, if it were $600, is $518.40. Okay, it decreases, so this is decay. The rate is 1.4%, so that is the same thing as saying 0.014. What's the initial amount? 120,000. Write a function. So the amount of people is going to be the initial amount. okay, is going to be that below 1. So let's see what that actually number is. So 1 minus 0.014. That's going to be 986. T. What is the population after 10 years? Okay, I'm going to plug in the number 10 for that T. Oops. Missed a 0 there. So that's 1, 2, 0. Let's go back to the calculator. 1, 2, 0, 0, 0, 0. To the 0.986 to the 10 years. One zero four two one nine. To the nearest whole number, it'd be 220. Okay, the population in the world in 2000 was approximately 6.08 billion. The annual rate of the increase of 1.26% at blah, blah, blah. Write a function. All right, here we go. The amount of people is originally 6.08 billion, 1 plus the rate, so that'd be 1.0126 to the t. What will it be in 2020? And I'm assuming t is equal to 0 is the year 2000. All right, so in 2020, t is equal to 20. So the population in 2020 should be 7.81 billion.